Hello. In this work, the main objective is to take a recording of any instrument, like the organ or violin, and transform it to a recording of the same piece of music, but interpreted by a piano. To do this, we must perform transcription, which consists in converting a music sound into a symbolic representation. This representation includes the start and duration of each note, the intensity at which it is played, as well as its frequency. Then, we must perform synthesis, which consists in generating an audio, given a symbolic representation of music. A crucial part of music transcription is onset detection, which is the process of detecting the beginning of notes. There are two approaches to onset detection. With a classical approach, the LibRosa algorithm detects peaks in the onset strength envelope. We compared the previous method with the data-driven methods proposed by MadMom. We used a CNN and an RNN architecture. As a performance metric, we used an F-measure score with a tolerance of 0.1 seconds. All three methods were run on a dataset with 321 human-labeled songs. The graph in the screen showcases the F-score obtained by each one. Because the CNN had a better result, it was used over the rest of the work. For estimating the tempo of the song, a LibRosa method was used, which measures onset strengths, and estimates the tempo from onset correlation. For velocity estimation, we considered a time window beginning just after a detected onset, in which we computed the RMS. The peak RMS is linear with the square of the velocity. The proportionality constant depends on the specific synthesizer, but fortunately, it isn't important, as only the ratios between amplitudes of different notes matter for a faithful transcription. For fundamental frequency estimation, we take a fixed-sized window after the onset and use it to calculate the DFT. By detecting the peaks, the fundamental frequency is identified, and the note with the closest frequency is selected. For offset detection, after computing the fundamental frequency associated to each onset, we continuously check its amplitude by taking the DFT at regular intervals over the song, called ticks. If the amplitude falls below 30% of the initial amplitude, we consider the note to be over. If the amplitude is greater than at a previous tick, we consider the previous note to have ended, and the same note to have been played again. We upload all this information to a MIDI file, which we will then use for synthesis. We crafted a method to assess the quality of the music transcription, which uses the MIDI file associated to a certain piece of music to obtain a ground truth. Our metric assesses the ability of the system to predict the played notes, their duration, and their velocity. The error metric for each feature consists in the root mean squared error, taken only on the correctly detected onsets. The issue of automatically getting the ground truth from MIDI files is very important, as it can save lots of resources when it comes to generating a data set that can be used for data-driven methods. In the synthesis part, we take a MIDI file and use its information to generate a grand piano sound. We decided to use MIDI files as the input to our synthesis process, as these are very common. The synthesizer takes the sustain pedal into account. In this work, we seek to reproduce the sound of a grand piano. The plan is to take a set of recordings of individual notes, process them according to the desired amplitude and frequency, and then play them back. We use 3 different recordings for each note, a loud one, a medium one, and a soft one. The piano recordings were produced by the University of Minnesota. Some of the notes started some seconds after the beginning of the recording. So, we had to perform onset detection and crop the note accordingly, such that the onset lies at time 0. All such transformations had to later be checked by a human. We don't use recordings of all 88 notes. Instead, we use a recording of a note every 8 semitones. When we want to play a certain note, we find the closest recorded one, pick a dynamics, and then resample the recorded note to adjust its frequency to the desired one. To decide which recording to play back, we use a simple KNN method, which associates an input frequency and an amplitude to a dynamics, i.e., pianissimo, mezzo forte or fortissimo, according to the data we have available. Next, we will hear the results of our synthesizer.